Welcome, guys. So in this video, I want to talk about Grover's algorithm. What I plan to do in this video, because that I have seen many other video about Grover's algorithm, and but I think some of them is really complicated. So I want to present my own version of the Grover's algorithm, or basically my own interpretation, and hopefully then it will be easier than like the Wikipedia or something. So okay, so before I start, let's quickly subscribe. Please make sure you subscribe to my channel. Okay, so let's talk about introduction, right? So suppose that you have a function. Basically, if you have a bit string, right? You have a bit string. So 0, 1 to a power n means that you have a bit string and a map to bit string. So that means you have a classifier that if somebody give you a bit string, then you can say, oh, the result is f0 or not. Okay, and then we are assuming that only one of them. So only one of length x will have fs is 1. Otherwise will be 0. So the problem is like suppose you have a box, right? And in the box there are many balls, right? But only one ball is marked, so this is x. And you have a classifier f that if f see this x, then it will produce 1. Say that oh you find the correct position, you find the correct object. Okay, and so the question is that how many queries you need to find x. Okay, so generally, if you see a classical algorithm, or I mean, somewhat that the naive algorithm is that basically you pick up 1 and then you see whether this is correct, and if it's not, then you pick out 2, right? So by definition, the complexity is just n, right? Suppose you have n balls, okay? So the idea of the quantum algorithms is that you can find a algorithm, right, by quantum computer such that it is square root of n queries. And in the rest of videos, I will present algorithm, and in the next video, then I will prove that the square root of n is optimal solution. So there's no other quantum is optimal solution. So there's no other quantum algorithm or other quantum classical algorithm which you can prove, which you can show that square root of n is, which you can find another solution which is better than square root of n. So if you are like the complexity guy, then you can use the omega notation. So in general, you need O n queries, and optimal you need omega n queries, square root of n queries. Okay, so let's talk about algorithm. So there are many ways that people present it, right? But I want to present it very easy. So our starting point is phi will be just all the superpositions. So I think everyone knows about what I'm talking about, right? So suppose you have n balls, right? You just use phi and combine all these. So you view each ball as one state, and span a vector space, and you say that phi is just the square root of a linear combination. Okay, and then these things we have f of x, right? So we have this f. So I create I suppose that we can create a quantum channel. The quantum operations called f, right? And the f is x on I. Okay, so maybe I call u. So u is somehow like standard notation. So I use ui. So ui will be, so I use x. Label x means that ux is only work for x, right? So ux x on I will be minus I, and f of x I. Okay, so don't be afraid. This USI just tell you that it will give you -1 if x is the correct guy. Oh, sorry. What I'm writing about. If I is x, right? So if I is x, then you use -1 I. So now you can write x. Then if I is not x, then you use I. Okay, so this is one can create linear transformation quantum operation U, such that it satisfies property. Okay, and now we create another operation called V, right? Since we have phi, right, so we can create a V called it by phi minus identity. Okay, so we have the one states, and the two operations, Ux and V. Okay, so let's describe the algorithm. So algorithm. So if you see the Wikipedia, there are, I mean, many people will say too much, which is so complicated in draw diagram. So I don't want to draw it. So the idea is that first we start with phi, and the second is that we just act Vux by k times, and the third is just measure in a computational basis. So done. So this is the algorithm step. So first we start phi, right? So we have already has our cute phi. And the next we just use Vux on k times. Okay, so k will approximate to square root of n, and the measure in a computational basis. Okay, so before we do the analysis of algorithm, let's create a small section. Just do some simple calculation to make sure that we will not have trouble. Okay, so let's do a simple computation. Suppose let's say Ux econ phi. So what is Ux econ phi, right? So what is Ux, right? So Ux will be this guy, right? Ux, and another way to, so you see another way to write Ux is write Ux as 2 minus 5 this, sorry, can be written U as this okay, so maybe I can write as this, right? So let's try this. So I can write Ux as 1 minus 2xx, right? So let's say if Ux econ I, then if I is x, right, then you will get the x minus 2x x, right? So this and x, right? So this turns 1, so we got minus x, right? And if Ux econ I, this is I equals x. If I is non-x, then this guy is 0, you got I, right? So I can write Ux phi as this guy, right? So how about Ux phi? So simple calculation, x econ our beautiful phi will be phi minus, right? So x is only one, is the only one component, right? So this will give you a 2 divided by square root of n x. Okay. How about our v econ our phi? So v is phi is identity, so 2 phi minus phi, right? Phi. And then how about v econ x? And a simple calculation, you get a 2 square root of n phi minus x. Okay. And also Ux econ x is just minus x. Okay, so these are four ingredients that we will use. Okay, so we can start to do our calculation. Okay, so calculation is basically we need to start. So we start our phi, right? So the important is that we need to see how Vux econ phi. Okay, so this is the first time. Okay, so let's do the calculation. So that's Hilbert space can be as a span of x and then a complement of x, right? So complement of x just the other basis. So I just separate my Hilbert space from x and the others. Okay. So one can write phi as some x. Let's say sine theta x plus cosine theta x complement. So S complement is a vector space. Okay, and by definition, right, x econ phi will be square root of n. So sine theta will be 1 over square root of n. So you don't need to care about this cosine sine cosine. You just we only need this. Okay. Let's say how to write Ux as a so now I want to write the operations as the x and the x complement. So Ux, right? We know that ux econ the let's say ux econ x will be -1, right? So this guy will be -1, 0, right? So this is basis x and x complement, x and x complement. Okay, and for x complement, then what? Then this is exactly the same, right? So it's 0, 1, right? So our v, by definition, v is 255 minus 1, right? So v will be cosine just 2 times the. Okay, so let's maybe do it step by step. Okay, so what is this guy? So this guy is just 2 sine theta x plus cosine theta x hat sine theta x plus cosine theta x hat x complement -1. So this is identity. So combine all this just, let's say 2 cosine square -1, 2 sine theta cosine theta, 2 sine theta cosine theta, and then 2 cosine square -1. So this is -2 cosine 2 theta sine 2 theta sine 2 theta cosine 2 theta. Oh, sorry. Oh, this is sine. Sorry. Okay. So we have the u and v. We have the u and v, right? So everything now is clear since we already have u and v. So simple calculation, vux will give you cosine 2 theta sine 2 theta minus sine 2 theta cosine 2 theta. Okay, so you see this is just rotate. If you have, so this is if you use xy plane, right? So you just rotating 2 theta angle. That is a geometrical meaning, right? So let's in let's mean in x and x complement basis, they are just rotating 2 theta, right? So this is the operation of vux, the property of vux, right? So the simple idea is that vux to the power k will be just cosine 2k theta sine 2k theta minus sine 2k theta cosine 2k theta. Okay. So our starting point phi in the x and base is just cosine and sine, right? So sine cosine, because I use the right. So because the first component is x, the second component is x complement. So now everything is clear. So the resulting states. So after finish my our calculation, this vux to the power k econ phi will be just cosine 2k theta sine 2k theta minus sine 2k theta cosine 2k theta econ sine theta and cosine theta, right? So okay, so the result will be very easy. So the first thing is basically sine 2k plus 1 theta, right? Because you get cosine minus cosine sine plus cosine sine, right? So you get this, and this guy is 2k plus 1 theta. Okay, so you can measure in a computational basis. Okay. Then so if you measure in a then you will get a probability of getting x, right? X will be just sine square 2k plus 1, right? Theta. Right, just square of the first component. And we want this guy to be as large as possible, right? So we hope 2k plus 1 theta should be what? Should be pi over 2, right? So sine theta is 1 over square root of n, right? So the beginning theta, when n is not large enough, then theta will be close to 1 over square root of n. So 2k plus 1 theta square root of n will be close to pi over 2. So from this we can prove that k is approximated pi over 4 square root of n, right? So pi is like 3.14, but we don't care in a complexity theory, so we can just write it as omega n operations, or theta. So I should say the square root of n is sufficient. Okay, so this is the all the progress, all the simple calculation of Graver's algorithm. So actually, so all the Graver equations can be written as 3 lines. So the first line is just write on a computational basis, and that Vux k times, then the k should be approximate square root of n, then we will prove it, and then just measure a computational basis. So it's not like if you go to Wikipedia or something or the textbook that they write the Graver's algorithm that very long and very hard computation and lots of strange details. So in this video, I only provide the minimum information and the minimum details that you can prove. Sorry, right? So our recall is just let's first create this v and ux, and then we compute v and ux and go to the case power, and then finally we act on this phi, and we take the probability, and finally we can easily prove that square root of n is sufficient. Okay, so next time we will prove that square root of n is optimal, and I will see you guys in the next video. Be sure to subscribe to my channel. Thanks.